Okay, welcome to lesson 28. This is the second lesson on actuators. So I'm going to start by just doing a little bit of review of what we've talked about previously. Again, this is our closed loop mechatronic system diagram. We're in the realm of looking at actuators right now. So we're talking about that today. As I said last lesson, we're going to talk about the types of actuators that are highlighted in red here. Today, we're going to continue our discussion of electromechanical motors, and that's because they're just the most pervasive type of actuator. But then we're actually going to have some time to talk about some different types, newer, more exotic piezoelectric and shape memory alloy actuators. And then in our third lesson on actuation, we'll talk about some hydromechanical actuators. Okay, so to review, we talked about this last lesson, permanent magnet direct current motors, and we were able to develop these constitutive laws for those equations. Remember, we started with the doing KVL and looking at the circuit for an electric motor, and that gave us this equation, which is a time varying equation. Then we made an assumption or said, we'll just look at the condition when it's at steady state. So the time varying term goes away, and that simplifies to this equation. We rearranged that equation so that we could get our torque speed curves, our torque versus speed load line equation. And that's plotted over here in these plots. And recall, this is really a family of curves that varies as we increase voltage. So, and this would track with any personal experience. If you take a motor and increase the voltage on it, it will speed up. Okay, it will move along this horizontal axis up until a point where you reach the limit of the motor. Okay. We went through an example problem where we looked at, we needed a certain, if we had a certain type of motor and we applied a certain voltage, how much torque could it develop? So take a look at that again if you're not sure how that worked. Okay, so today, some new content here. I want to talk a little bit about dynamic performance or dynamic effects. If we didn't zero out that dynamic term, if we were interested in the motor turning on, turning off, or speeding up, slowing down, we're going to have this dynamic term, this voltage changing as a function of time due to the inductive properties of the windings of the motor. For our purposes in mechatronics, what we need to think about is the fact that this changing current as you turn, if you speed up a motor or slow it down or turn it off or turn it on, it creates these inductive effects with the windings, which we're not going to go into detail on the physics of why it happens, but you should know that it creates a strong reverse voltage, which could damage a transistor if you're using a transistor to turn the motor on and on, which we will. So in the lab, we will build a circuit that looks exactly like this. And if you shut the motor on and off really fast, you could damage that transistor because you can be reverse biasing it. In this configuration, there's a positive voltage here. And if we shut the motor off quickly, the collapsing magnetic field will cause a strong, excuse me, let's exit out of this. Okay. Should still see my screen. I just want to write on this slide. Normally, current should be flowing through like this. Okay, that's the normal condition because this is plus voltage up here. But if you shut the motor off really quickly, you're going to get a big current flow going the opposite way through the transistor. Basically, positive here and negative here. That's going to suck current through this in this direction, which can break our transistor, and we don't want to do that. So engineers get around this by putting this diode right here. We call it a flyback diode. So when the motor is operating in the correct way, so when current is flowing in the positive direction, it can't go through this route because the diode would prevent it from going that way. It's a one-way valve. Then when the motor shuts off and that collapsing magnetic field tries to suck current back through the motor, that green line, the current will want to go through the diode because it will give it the path of least resistance. And so that will allow current to flow from this positive side of the magnetic field here to ground without having to travel through the transistor. So what we get, I'm going to erase all this junk here. Whoops, trying to erase it. Here we go. Come on. So instead, what we'll get, when that magnetic field is collapsing, current will go this way through the flyback diode to ground safely, and will avoid the whole transistor altogether. So that's something you want to make sure you include anytime you're setting up a circuit with a motor that's going to be powered by a transistor, and the motor is going to be turning on and off. Now, you might ask yourself, why would we turn a motor on and off really quickly? Well, we do that a lot with pulse width modulation, which we've learned about before, and we'll talk about that in a second. Okay, another thing I mentioned in class, I mentioned in the last lesson, most DC motors will have a gearbox attached to it because usually we want the motor to run much slower than it naturally wants to run at. So we usually gear it down to slow it down and increase torque. Keep in mind that your gears will add inefficiency. There's friction in there. We could hear that when we hear the gear motor run. So keep that in mind. Now remember, we talked about how a motor is more efficient running at it at a higher speed. So if this is our torque speed curve, just use a capital T there. So torque, messing that up. This is our torque speed curve. The max power is at the halfway point. So if we drew power, it would look like this, basically a parabola. That's not a great parabola. Okay, making it worse. Efficiency looks kind of like this. It goes like that. So we're usually most efficient at a high speed like that. Okay, and these are not to scale or anything, but the point is to show that higher speed is more efficient. So we usually want the motor to run at high speed, but for our application, we often want it running slower, so we add gears. Okay, I want to briefly talk about a couple different types of motors. What we've been talking about before were permanent magnet DC motors. Well, now what does this say? This says wound field DC motors, so not a permanent magnet. So the advantage of a permanent magnet motor is it's lightweight, it's small, it's simple, easy to operate. But in these motors, we have, instead of magnets providing the electric field in which the rotor is going to interact with, we've got another electric field that's providing that. So here, this sketch shows what a PMDC motor would look like. There's a permanent magnet, and it's interacting with the rotor that is getting that kind of changing current to get a changing magnetic field. In a wound field motor, instead of a permanent magnet, we have another coil of wires that's providing that additional magnetic field. And this can be done in a couple different ways. The most common are shunt and series wound. So in a series wound, let's see, so this is a shunt wound. This is basically parallel. So the current is flowing through the motor rotor like that, and is flowing through the wound field in a parallel direction. In a shunt, they're going, or sorry, in a series, current's flowing this way through the coil, then it's making a turn and going that way through the rotor. So, okay, who cares? Well, let's look at, and this would be really interesting if you're into designing motors, which we're not going to do, but what I want you to be aware of is the fact that these give you different characteristics. So this is the shunt wound. So in this case, this is where the current is flowing in the same direction in both motors, okay, or in both fields, sorry. So that's current through the rotor, that's current through the field. Look at this shape of this torque speed curve. So normally for a PMDC motor, we expect a straight line, right? What we get here is this line that's fairly flat for a long range. So what this means is, for a wide range of speeds, we can get fairly consistent torque. So consistent torque for a wide range of speeds. And so that can be really useful for lots of industrial applications where you might be wanting to change the speed of how the motor's operating, but still be lifting a load or providing a torque that's similar. You don't want the torque changing constantly with your speed. Okay, series wound is another, gives you another different characteristic. Okay, so again, remember a PMDC motor would have that straight line. This is anything but a straight line. It's almost looks like the opposite of the last motor we saw. What's nice about this is it can operate at a very low speed with high torque that is consistent. So notice this, we get consistent torque at a low speed. So this is really nice for things that need to start from zero and get moving. So for starting heavy load, so think about a winch or a crane that needs to lift something and it needs to operate pretty slowly but have high torque. So those are some different applications. Okay, so as far as DC motor control, we can run motors open loop, we can run them closed loop. Open loop means we're not getting feedback, we're not really controlling how fast it runs, other than we could have information about the motor that tells us, okay, if we run it at say 3 volts, it will go a certain speed. And then we're just hoping that it goes at the speed that we want it to go at, that we've designed it to. Closed loop, you're sensing the speed or the position and you're adjusting your input to get what you want. Okay, now we've talked before about pulse width modulation, and that's what we'll use in our lab to control the speed of the motor. Again, why do we use pulse width modulation? Well, what is pulse width modulation? It's instead of giving it just a constant voltage like this, we give it pulses of voltage. We give it maximum. So this is max for some period of time. Then we give it nothing, off, 0. And we give it either all the way on or all the way off in pulses. And we do this because it's more efficient. We get more efficient operation through the transistor. We talked about that before. So, here's our transistor. We're going to use a transistor to turn this on and off. We lose the least amount of voltage and current in the transistor if we do it this way. Okay, so and that goes back to when we're talking about using this flyback diode. We're going to use a transistor and we're going to do PWM here at our input to turn the motor on and off rapidly. That's going to be constantly creating that back EMF, which could destroy the transistor. So we need that flyback diode to avoid that damage to the motor. Because even though that PWM is happening at really high frequency to us and we can't see it, it's not at a high frequency to the transistor and the electrons in there, and they will damage the transistor if we don't have that flyback diode. Okay, so we will control a DC motor with PWM, which is the most efficient way to operate it. Because this is so prevalent, we've developed devices to help us do this. So this is an example of what's called a 555 timer, which allows you to easily create PWM outputs that can range. You can control the frequency, you can control the duty cycle very easily, and we will use this in the lab to control a DC motor. So if you're here are some equations for how it works. Now, if this is, so T1 would be the on time, when the duty cycle is high, and T2 is when the output is low. So how do we control these? If we know we want our motor to operate at a certain speed, we can just use fixed circuit components, R2 and C1, and this is how it would look in a circuit, and we get a constant duty cycle output, pulse output. In reality, we probably want to be able to adjust the motor speed. So we have these parameters, we have R1 and R2. If we use, for both of these guys, and that's these guys right here, if we put a potentiometer in here, we can turn a knob and control the relative ratio of R1 and R2 and be changing the duty cycle. So guess what? That's what we're going to do in the lab, right? And that will be pretty cool when you get that working. Okay, finally, last lesson, I hinted at a way to change the direction of the motor. So remember, for our microcontrollers can only output positive voltage. So for our micro is positive voltage only. So how do we get the motor to turn in different directions? Well, this is called an H-bridge controller. So it's shaped like an H, and we have 4 transistors, 1, 2, 3, and 4 here. Or these could be switches, but in practice, we're going to use transistors because we can digitally turn them on and off. And these would be like the bases right here, which control whether the transistor is on and off. So in this case, if you want the motor, this says motor forward, we're turning on 2 and 3, and current can flow through 2 and 3. It will flow this way, through that way through the windings of the motor, and then through number 3 to ground. And that will make the motor spin forward. If we want it to spin backwards, we shut down 2 and 3, and we turn on 1 and 4. Now current goes this way through the windings, and we see that is the opposite direction of how it flowed in the other case. So that way we can control the speed of the motor. So combining an H-bridge controller with pulse width modulation, we can control both direction and motor speed. Okay. All right, so now I want to move on to a new type of motor. This is a brushless DC motor. So these are kind of the latest and greatest in small motor technology. These are used in situations where performance is very important. So a great example of that is a quad rotor UAV, or any kind of flying UAV if it's like a fixed wing aircraft. Because we want high power and low weight, and we call that power density. So we want a lot of power for a low weight, and brushless motors give us a huge improvement over a permanent magnet DC motor. So for one thing, we have a lot more control, and we waste less energy. So just in speaking in general terms, a brushless DC motor has these characteristics relative to a DC, a permanent magnet. So this is like versus a PMDC. Okay, so less wear, because in a brushless motor, there are no parts in contact that are rubbing against each other. You do have a shaft that's riding on bearings, but you don't have, remember in the permanent magnet motor, you had brushes that were basically sliding across a commutator. We don't have that. So no brushes. That's why it's called a brushless motor. So because of that, you get less noise, we get less arcing or no arcing. And we didn't really talk about this, but for a PMDC motor, its speed is limited by what's called brush bounce. And that's just the dynamic characteristic. Those brushes sitting on the commutator are going to vibrate as it moves faster and faster. And at some point, those things vibrate so much that they lose contact and can't transmit power to the rotor. So we eliminate that with the brushless motor. No brush drag and friction. Now, okay, there's always a cost, right? So it's more expensive and it's more complicated to control. A brushless motor, you can't just hook it to a power supply and expect it to turn. It won't turn. It will just stay. It will just hold its position. You need a sophisticated controller that is going to actively turn on and off power to these 3 windings here. Okay, so in that, now how they actually work is somewhat similar to AC motors, in that you've got a magnetic field that's rotating around the stator. So here, and the other weird thing is, so this is the stator, and that's where the windings are, and then the rotor has the magnets, and the rotor is on the outside of the motor. So in this case here, this motor, this black thing here is the rotor, and that's going to rotate. And if this were a UAV, you bolt your prop onto the end there, and I'll show those when we see each other in class. So to make this work, we have to switch current on and off around the stator to turn these various windings on and off in a certain sequence. And we'll talk about that really quickly here. Next. Okay. So this is a simplified version of a brushless motor. You usually, like you saw in this previous slide here, there's usually more windings than what we're going to see here. But this has 3 sets of windings, A, B, and C. And then notice, so the rotor is shown here in the middle. In reality, it's usually on the outside, but that's okay. This just makes it easier to visualize. So the rotor is a magnet with a north and a south pole. And we're going to run current through these windings to create complementary north and south pole magnetic fields in the windings to get the rotor to rotate. So in this case, we see A is turned on. We've got a north pole here and a south pole here. And so the south pole on the rotor wants to be attracted to the North Pole on the winding. So here we have positive current on the A winding. We have no current on the C winding, so it's off. And what's going on with the B winding? Whoops. So in this particular case, both B and C are off. We'll look at the next case down. And this here is a link to a video, and I highly encourage you to go see it. I'll put the link in the chat on the Teams page. So it should be below where I posted this video, and you can go click on it and check it out. But we'll look at that video in a second. So looking down here on this lower slide, in this case, we see A is off. Okay, so if you look at where the rotor is, A is off because we don't want A doing anything. We don't want it to be attracting. B is, well, this isn't the next slide. Okay, we're going to go look at the next slide, and then I'm going to go to the video. Okay, so here, what's going on with the current? A is off, B is negative, C is positive. So this is what I want to talk about. So it's already at A, so we're going to turn A. So presumably in the previous step, A was on and it was attracted to A. Now we're turning A off, and we're going to give positive current to the C windings. That's going to put a north pole right here and a south pole right here. So this north on the rotor is going to be attracted to the negative side of C, where the south pole is, and this south pole is attracted to that north pole. And then what's going on in B? B is negative. Negative puts a it's going to put a north pole here and a south pole here. What that does is it pushes the rotor away, because this north pole is repelled by this north pole, and this south pole is repelled by that south pole. So that pushes it away. Okay, so in this arrangement, both B and C are applying torque to the rotor. And so that makes it a little bit more efficient. And now, again, this is a simplified version. If we look at a real brushless motor, we see there's more windings. So you're using those adjacent windings to push and pull at the same time. And in the video, it talks about how we can actually design the motor so that we can reuse current. And so in this configuration, the current going through, if we've got positive current going through C, it's going to go through C, out negative C, and then into negative B and out positive B. So the same current will create a positive flow of current through the C windings and a negative flow of current through the B windings. So I'm going to show you this motor, this video really quickly. I don't know how sound will work on this. Okay, so hopefully that encourages you to go check out that video. It's pretty cool. It's about a 10-minute video, and it starts by talking about how permanent magnet motors work and how that's in contrast to a brushless motor. Okay, so, but the main takeaway I want you to get is the differences between those two motors. So types of motors. So quickly again, brushless motor is going to be less wear, more efficient. It's going to be lighter for the amount of torque that you can get. And the drawbacks are that it's expensive and more complicated to control. You need a separate controller, or a microcontroller that is programmed to be able to turn the motor on and off. Okay, so let's move on and talk about a new type of motor, and that is a stepper motor. So we've heard talk about this. We're going to play with these in the lab. This is another type of a permanent magnet motor. We've talked about brushed permanent magnet motors. This is your PMDC. This is brushless, which you just talked about, and then there's stepper. Earlier in this lecture, I talked about the wound field motors, and we won't talk about those anymore. So this is what a stepper motor looks like right here. This is your PMDC, and that's your brushless. So these are designed to be relatively precise open loop. So these are a couple different versions of what stepper motors look like. And how they work is somewhat similar to the brushless motor we just talked about. These, again, are like a brushless motor. You can't just simply attach a power supply to it and have it turn. That will not work. You have to turn on the different poles of the motor one at a time. So usually it needs to be controlled by a computer or some kind of programmable controller. There are a lot of places that sell motor controllers just for stepper motors. And there's lots that are designed for Arduino and designed for all kinds of different uses. So a stepper motor rotates in discrete steps. It does not just spin freely. It goes one step per input pulse, and those steps will depend on the design of the motor. They can range quite a bit. So we're going to use a pretty simple motor in our lab. I think it gets 16 steps per revolution, but you'll get motors that are hundreds of steps per revolution. So which are just going to give you that much more precision. You get torque and power similar to a conventional DC motor, but you get a high holding torque without overheating. For a standard PMDC motor, if you try to hold it in one position with current flowing through it, it's going to overheat and burn up. A stepper motor is designed to do that. So if you need to hold a load in one position, it's great for that. Now, where you have seen stepper motors is in 3D printing. These are super common in 3D printers to control the position of the print head, along like a belt system. So if this is like a belt and this guy's moving back and forth, the motors right here on the ends, there's usually like a pulley or something over here. This is going to be a stepper motor, and that's going to allow the system to precisely control the position of the print head as it's moving around. So how do they work? So here's kind of some of the insides. This is a very simplified version. Okay, so in this case, you've got windings around some magnetic material as we turn on a pole. So in this case, we've got this pole right here is turned on, and the rotor is going to be attracted to that pole. Okay. Then we turn on B, and this thing is rotated over there. And with this type of design, we see this is kind of offset. So we notice the rotor has 90 degree, is at a 90 degree angle here, and these outer stator windings are at 60 degrees. And so this allows us to get half steps in between the different phases. So in general terms, we'll turn on these windings in a certain sequence, and that will cause the rotor to turn around the stator. Okay. And because of the way these are designed with so many little steps, you can position the rotor at a certain position fairly precisely without needing any external sensors. So this is a more realistic view of a realistic stepper motor. Notice we've got many more little poles here that can align. And if you look at this diagram over here in detail, notice these are intentionally out of alignment, so you can use these half steps to get double the precision. In this case too, the rotor is in the middle here, and you've got a different arrangement of external stator poles to give you, again, more precision. Okay. So that's general operation, and you'll get to play with it a little bit more in the lab. So here's an example of a motor this is exactly what we're going to use in the in our lab 7 in the actuator lab. And again, because these are so common, they make devices to make these easier to use. So this is a transistor array that allows us to turn these phases on and off without having to wire up individual transistors for each phase of the motor. So in this arrangement of the motor, we provide a common power supply, and notice it's 12 volts. So the Mega doesn't provide 12 volts, so we're going to have to get that from an external power supply. Okay, and then we turn on the phases of the motor by turning on a connection to ground for that motor, and that's going to run through this transistor array. These pins are going to be connected to your Mega, so you can control the phases. So there are a few different ways to run a stepper motor. In the first example, this is the simplest to understand. So if we turn on phase 1, the rotor will align with phase 1. Then if we turn off phase 1 and turn on phase 2, rotor will align with phase 2. And so if we keep repeating this pattern, we see we can move around the rotation of the motor in 4 steps. Okay, so this would be, we call these full steps, but low torque. Now we can do something different where we still have full steps, but we have high torque by turning on 2 phases at a time. So now the rotor is going to position itself between the 2 phases, but we're going to have about a 50% increase in torque. Okay, so, and then we turn off 1 and 2, or we turn off 1 and turn on 3, and it will jump from here over to here, and et cetera, so on. Okay, so that gives us a little bit more torque, but more it will require more current. Okay, and then we can get more precision by doing half steps. Here we turn on 1, then we turn on 1 and 2, then we turn off 1 and only have 2, then we turn on 2 and 3, et cetera, and that gives us twice the position resolution as we had with the full step mode. Okay, and now what this would look like in turning on these pins 1 through, or here in this case it's 4, 5, 6, and 7. But if these were bits, we can output these to our pins as bits and control the motor that way. Okay, so with stepper motors, we can do open loop position control, assuming that the motor is going to go to the position that we command it. Usually the output is the angular position of the shaft, and we're going to have, if you're using a stepper controller, they will usually take controller. You can put in a pulse input. So this is basically like frequency of pulses or speed and the direction. Okay, you tell it what direction and how fast to go. And I'll show you what one of these looks like in class. Okay, so move on here. Okay, so that is stepper motors in a nutshell, and we will explore those hands-on in the lab. Okay, so final summary of the various types of electric motors. We talked about permanent magnet DC motors. These are your simplest to understand and to operate them. You just apply voltage. They're relatively inexpensive, relatively lightweight, but their drawbacks are they have brushes. That causes friction, noise, other issues. They're less efficient and therefore low power density. Brushless motors, more expensive, more complicated to control, but have less wear, more efficient. Now, if you're building something where weight matters, you might take into account the fact that that more complicated control means you need an additional controller to run that motor, which may not be to your benefit. But they make brushless speed controllers for motors for things like quad rotors and UAVs that are extremely lightweight. They weigh almost nothing, and I'll show you those too. And then we have stepper motors. These really you're going to choose if you want to be able to do position control, and you need to be able to hold a torque at a certain position without it overheating. Okay, so those are the situations where you're going to use a stepper motor. You're usually not comparing a stepper motor to one of these other 2 types of motors because they're so different and the application of them is so different. Okay, so that's all we're going to say about electric motors. Now I want to move on to some more interesting types of actuators. And the first one of those is a piezoelectric actuator. And I'll also talk about a shape memory alloy in a minute here. Okay, so a piezoelectric actuator takes advantage of the piezoelectric effect And from sensors, you may remember that is certain types of materials, if you apply an electric field, a voltage, you will get that material to change shape, to change size. Okay, so it deforms. So these are different. This is a photo of different types of piezoelectric materials, and I'll pass these around in class. There's a few different ways to make actuators out of piezoelectric material. So this is what I used in my PhD right here, and this is called a bimorph cantilever actuator. Yeah, it's written here on the slide. So the gray parts are piezoelectric material, PZT. Okay, you have one on the top and one on the bottom. You sandwich them together, and then you put something in the middle. It needs to be conductive and fairly stiff. Then you apply a voltage, so plus voltage here and a minus voltage here. And what will happen is the crystal on top will grow, it will get bigger, and the crystal on the bottom will shrink. And so that causes the tip of this actuator to deflect. And then if I rapidly change this voltage off and on, this tip of this actuator will flap back and forth and can go really fast, and you get quite a good range of motion with that. Show a video. So here's a video from my PhD work. This is one of my flapping wing micro air vehicle prototypes, and these are piezoelectric bimorph actuators here in the middle of them that's causing these wings to flap. And this was a test to test out some control schemes. So I'm making the vehicle roll back and forth by changing how I'm flapping the wings. Okay. So there's a few other videos here that I'll show you in class. So that's one way to make an actuator out of piezoelectric crystal. Another option is, I say up here, I show stacks. Stacks is very simple, but you just have basically a block of PZT material. You apply voltage to it, and it grows. It gets taller or shorter. You're not going to get very much range of motion with this. The bimorph design allows you to get a little bit more range of motion, but obviously less force. This will give you pretty good force, high force. Another option is this inchworm, and that's shown here. You can make piezoelectric crystal, if shaped a certain way, vibrates in the shape of a wave like this. And this wave will travel through the material. And these little guys act like feet and can push this rotor to the left. And this is a motor, this is called an ultrasonic motor and camera lenses use these to move the focusing ring. So Canon, the famous lens manufacturing company, invented this type of motor to control the auto-focusing mechanism inside of a camera. And they're super fast, very quiet, and very precise. So those are pretty cool. All right, so just some general characteristics of a piezoelectric actuator. They have a relatively high energy density and power density. So for their weight, they can move a lot. So move fast or move at high force. They operate at very high frequency. They're very efficient, and we don't waste a lot of energy. They can produce a high stress, which we think of as force, so meaning force per unit area, P over A type stress. And they can operate in harsh environments. They're basically an inert type of material. They won't react with other materials. Now, the problem with piezoelectrics is strain. When I'm talking about deformation over length type strain. So they do not deform very much for the size of them. So you have to figure out these clever ways to magnify their displacement. That's why we have these bimorphs or these inchworm type actuators. So depending on your application, that can be a showstopper if they don't move far enough. They also require a very high drive voltage. For my flapping wing micro air vehicle, I was using about 200 volts, plus or minus, which is a lot, right? Obviously, your microcontroller isn't going to produce that. And this is one of the big hurdles to doing free flying micro air vehicle flight, is that it's difficult to produce voltages high enough to run these actuators. It's easy to do benchtop experiments, and if you noticed in the video, there were little wires connected to my actuators. But as far as like a free flying vehicle, that's going to be difficult. Okay, let's talk about our last thing here, and this is shape memory alloys. So this is also known as SMAs for short, easier to say. A shape memory alloy is a type of material that goes through a phase change at a certain temperature. So for those, if anyone is a materials expert, they might know more about this than me, but we're taking advantage of the change in state from martensite to austenite, or austenite. There should not be an S right there. That's a typo. There we go. So at a certain temperature transition, the material will change for those two states. So we see in the austenite state, the molecules are very nicely and neatly arranged, but they take up more space. In the martensite state, the molecules are more compact. So the material gets either more voluminous or less voluminous, depending on the state that it's in. And there's a number of ways we can exploit that property. So shape memory alloys can be used in multiple different ways. One way is that the material is trained and can go into a certain state. So you turn on a voltage and it will pop into a certain state that may be useful. As far as using it as an actuator, the most practical way for us to use it is as a shape memory alloy wire. And so this is just what it sounds like. It's just a wire. We apply a voltage to it. It changes size. What happens is it usually will shorten. Now, I'm gonna, let's see, draw an arrow like that. This will shorten. Now, you maybe, if you're paying really close attention, you're saying, okay, wait, he said when it gets hotter, the material gets larger in volume. Well, so what happens is if this is in the shape of a wire, the diameter actually increases when we heat up the wire. So the wire gets wider, and what that does is it causes the ends to pull in to create that change in diameter, and so the wire shortens while the diameter gets bigger. So what you need to know is V, positive V change to relates. Applying a voltage causes the wire to shorten. Okay, so what are the takeaways for this? For our purposes, we want to remember that a shape memory alloy has a very high energy density. These things are very, very light. We're gonna use these in the lab, and you're gonna see these are like a hair. They weigh nothing, and so you can get some actuation with something that weighs almost nothing. So that's pretty cool. They only require a low drive voltage. So compare that to the piezoelectric, which needed like 200 volts. These things will run on just a couple volts. So very easy to use with a microcontroller. They're very efficient. We don't lose a lot of energy with them. They can handle a high stress, so they can produce a relatively high P over A, force per unit area. They're silent. They make no noise. Now, here's the major drawback right here is frequency. These things are slow. The piezoelectric crystals on the previous slide, these things, I didn't write this down, but this can go like tens of thousands of hertz frequency moving back and forth. Shape memory alloy, you're going to test this in the lab, but you're going to find out you're lucky if you can get about 1 hertz of cycling. Now, that may not matter if all you need to do is use this one time. Say you've got a UAV and you want to pull something to open a latch to drop something off your UAV. This would be perfect for that. You only need to use it one time. If it's not super important that you get the timing of the release really precisely, then this can work great. The other issue is that these experience hysteresis, which we talked about before. Remember, hysteresis is that thing where it follows a different path on the way up than it does on the way down. So it might look like that. Okay. This link takes you to an example of using shape memory alloys in a project. Okay, but I don't want to do that right now. Instead, I want to show you, here's an example homework problem. So Jimmy Capstone needs an actuator to release a device on his UAV. Actuator must be able to apply a force, a 2-pound force, and it needs to have a range of motion of 2 millimeters. Help him select a Flexinol wire. So Flexinol is a company that produces shape memory alloy wires. We're going to use these in the lab, and this is their published data. So what we see here, notice things to look at: diameter of the wire. So they sell their wires in different diameters, and this is given in inches, which is kind of annoying. We see that for different size wires, we get the wire has different resistance. Notice resistance goes down as diameter goes up. We get different pull force based on the size of the wire. Okay, bigger wire, bigger pull force. That's because of stress. Okay, and then we see some temperature that needs to actuate at, and then this is just some performance characteristic, like kind of how fast can it move. So we're going to want to focus on this diameter and pull force. Okay, so how do we do this? So let's go on to the next slide here. Okay, so I've just summarized what we need from the previous slide. So we're going to start with, the way I look at this is, let's start with the force we need to apply. Okay, so we know that stress equals P over A. Okay, so that's 2 pounds. And we want to know A, so we can sub in what we know. So we're going to rearrange this equation. That should be an equal sign, right? So we get A equals P over stress. We were told that this particular material has a stress of 170 MPa. So we can go, we need to convert 2 pounds into newtons. So 2 pounds is 8.9 newtons, sorry, 8.9 newtons. You can verify that. So if we go 8.9 newtons and we have 170 megapascals, so that's times 10 to the 6 newtons per meter squared, and do the math, that is a 6. We get 5.24 times 10 to the negative 8 meters squared. Well, that's not very useful. Our chart is in diameter in inches. So we need to, remember our area equals pi d to the d squared over 4, and then solve for d. This translates to a diameter of 0.25 millimeters, which is, remember, a millimeter is, or 25 millimeters is an inch. This is about 0.01 inches. Okay, so that puts us down here on this, whoops, that table right there. Okay, or that row in the table, and that's 930 grams. So that's almost a kilogram. Okay, as far as, so that tells us what diameter we need. And then the resistance for that would be 1/2 ohm per inch. So its resistance is 0.5 ohms per inch. Now we need to figure out the length. What length do we need? So remember, strain equals deformation over length. Okay, and we're given a strain of 5%. So we want to solve for length. So we want to rearrange this so we have length equals deformation over strain. So desired deformation is 2 millimeters. The strain is 5%, so that's 0.05. And so that tells us we need a wire that is 40 millimeters long. Okay, and in inches, so if we divide by 25.4, that's going to be about an inch and 2/3 or something like that. Okay, so as far as resistance, what would the resistance of that wire be? Well, we know we've got 0.5 ohms per inch. So R equals 0.5 ohms per inch. So we multiply that by the length, which is 1.57 inches. That's what this equals. We get 0.785 ohms. Okay, so why are we calculating resistance? Well, if you're going to put this in a circuit, we need to know you're going to have a voltage source, right? You're going to have a current limiting resistor, and you're going to have your SMA wire. So you need to know for the wire you're using how much resistance it has so you can pick your current limiting resistor. Okay, and you're going to do that in the pre-lab for the lab. Okay, so how much, if we want a certain amount of current, so say we want current to be about 1 amp, then we can use V equals, Ohm's law, V equals IR. We just figured out what R is, plug that in, and you get a voltage of about 0.785 volts. That's pretty cool. Jimmy can actuate his thing from his UAV with less than a volt of power. So he could use a very tiny battery, or he could just use an output from a microcontroller. Okay, couple things here. This is a chart I actually had in my PhD dissertation where I just compared some different types of small, lightweight actuating materials. So this might be useful to you some point in your life, maybe in a capstone, in a situation where you need to actuate something. This just compares. So we just talked about the shape memory alloy and the piezoelectric. So if we compare blue to green, as I mentioned, frequency, shape memory alloy is really bad. PZT is very good. Energy density, shape memory alloy is very good. Stress, shape memory alloy is very good. And for strain, so length of actuation, PZT is bad. Okay, PZT right there. Okay, your textbook has this awesome chart that compares different types of actuation. Study this chart. I'm not going to go over it right now, but as I said multiple times, what I really want you to take away from this course is knowing when to pick one thing over another thing. Okay, so this is something that I would definitely test you on in the GR. Give you a scenario and you tell me what type of actuator is most appropriate for it. So we've got SMAs that we talked about today, piezo actuators, hydraulic actuators we'll talk about right before the GR. And that's pretty similar to pneumatic actuators. We've talked about servos. This is servo valves, which is something different. And we'll talk about those during the hydraulic lesson. All right, that's it. See you in class.